Okay, so first things first. Last night you may have seen that the homework server crashed hard. It was actually one of your colleagues who did that. Somebody from the other section, as it turns out, who will remain nameless. But that person actually ran a program that took up all the memory on the homework server, similar to what happened a couple times ago, and it went down hard. So what we're trying to do is we're trying to figure out a way so that, let's say I figure out something's going wrong, like somebody emails or Piazza posts that says something's wrong, I can go in and kill your jobs. Basically, it's kind of tricky to do because the only person allowed to kill your job is you or a root system administrator, and they won't make me a root, so that's too bad. But there is a way. I believe we've figured out a way. It just may take a few iterations to figure it out. But hopefully that won't happen again. And we've talked to the person involved, and I'm not sure what he or she did. But hopefully it should be OK. Somebody sent me an anonymous feedback on commenting. And I appreciate the feedback. And the feedback was basically, hey, look, there's lots of different commenting styles. If you're going to take points off for commenting, can you maybe give us some guidelines for how you actually want commenting done? And I think that's a very fair comment. So we are in the process of putting together some guidelines that you should follow for commenting. And the way you comment your own code can be very different than the way you're going to comment for the class. It should not be overly burdensome, but it should be something that we kind of all agree on a fairly good standard. So we'll have that out hopefully by tomorrow. I'll try to print it out. So if you want to re-provide with new comments, no worries. OK? So thanks to whoever did the anonymous feedback on that. Any questions? Yeah, Isabel.
Can you provide homework 3 or homework
4.
4? Okay.
Yeah, the new one. The last one, if you really think, hey, I commented in this style and I got points off, that's not fair, email me, I'll discuss it. But if I see a function, there's no comments in it, I'm going to say, well, you deserve to lose points. Right? So if there's nothing there, you deserve to lose points. So generally, we expect some comments in functions. Other questions or comments before we get going? Yes.
The comments that you provide us in the functions to guide us on how to
Yes.
if we kept those.
If you kept those, that's fine. I'm normally not going to care about the functions I create. If I don't comment them, that's bad on me. I should probably comment them better. But your own functions should have comments in them, the ones that you create. Yeah. Or any new code you create, if there's something that needs commenting, comment it. I mean, that's nebulous. We'll try to make it a little more explicit. OK. What else? That's about it? OK. All right, so here's what we're going to do today. We're going to cover 2 things today. First thing we're going to cover is we're going to finish up talking about tries, which again are one of my favorite data structures because they're pretty cool in the way they get implemented. We will practice tries on the lab next week, and you'll get a little practice there. You may, if you want, use a try for some of the later projects. In fact, the last project last year, some people all used a try, and it worked out all right. It was an interesting idea. It worked out fine. So if you want, you can do that. And then we're going to start on this topic called priority queues. And we're going to go into a little bit of detail on what a priority queue is. It's another abstract data type. You can implement it various ways. In fact, today we're going to implement it 2 ways. Next week we're going to implement it a 3rd way, in fact, a better way next week. And we're going to talk about what the whole idea about priority queues are. OK? Back to tries. So the other day, on Monday, we figured out, hey, there turns out there's a better way of representing words in a tree format than by word. Okay? If we break them up into characters in the individual word, then we can actually do something like this, right? Where we've taken cow and corn and we've said, let's go letter by letter and stick that into a data structure, this data structure called a try, and you end up doing this. Every node of a try in this try has 26 possible children. Okay, so we'd better figure out how to represent those and a good way to represent those. But that's how it actually ends up looking. Okay? If we put lots of words in there, we end up with a try that looks something like this. Okay? Fire, cow, red, pit, corn, sand, day, snow, pits, and fish are represented in this try as follows. Okay, what did we say the star means? End of a word, right? So both pit and pits is in here, right? Is the word, let's see, is the word, not really a good example. Fir, F-I-R, is that a word in here? It is not, because there's no star. If we added fir, it would add a little star there, and that's how we'd know that it was in the try. Okay? Questions on that idea? That's like review from last week, or from Monday. Okay. All right. So let's talk a little bit more of details. We briefly mentioned, hey, this is going to actually help our case here in terms of the asymptotic complexity. Okay? If you look at this, actually, if you're reading it, you're getting to the punchline, but that's OK. If you look at this, how many how many iterations do I have to do to find if corn is in the try? How many? Well, how many different? I have to look at C, then I have to look at O, so that's 2, and then I have to look at R, and then so 4 total, right? Which happens to be the length of the word, right? Do we care how many words are in the try to know how many things we have to do to search for corn? We don't. So this is actually, in this case, it's for corn, it is actually, what order would it be explicitly? What asymptotic behavior would corn be explicitly? Oh, how many did we go through? 4. Oh, 4 for corn. And what do we say when we do with constants like 4? We ignore them. So this really is order 1, meaning this is a constant behavior search. If you put a billion words, if you put the entire dictionary, which doesn't have a billion words, but if you put the entire dictionary into a try, to search for corn would take you 4 steps. C-O-R-N. That is really cool. It's a constant time lookup for any word in the try. Okay? There are trade-offs, right? There are definitely trade-offs in terms of the space required, right? There might be more space required for a try than an equivalent binary search tree. But sometimes sometimes you say, hey, look, I have plenty of memory, and I want to make the search really fast. Okay? There are ways to minimize the amount of memory, too. We'll talk about that. So it's not based on the size of vocabulary. That's good. We don't have to balance this either. There's no way to make a try somehow go keep going down in one direction such that you have to keep search, right? The biggest word that I know of is supercalifragilisticexpialidocious, right? Which is like 30-something letters. That would take 30, it would take 30 different iterations through this thing to actually find that. That's it. That's like the max, right? And most words have like less than 10 letters. Most do, right? So pretty cool in that sense. All right. So we said the complexity in here is based on the number of searches. Now, we are forgetting one thing. You do have to figure out what to do about going through, or in some however you set up your children, you have to figure out the comparisons there. But we'll talk about that in a second. Okay? Questions on the complexity of tries? They're awesome, right? Yeah, here we go. We ignore the complexity of the word, the comparisons, but that actually doesn't add too much to the picture. Yeah.
What kind of comparisons do you mean?
Well, yeah, right. Well, basically you say, look, is C one of the children of the original root, right? Is O one of the children of C? That's a comparison in some sense, right? So we're ignoring that for now. Okay, and it's not a huge big deal. But so what we have to really talk about is how we're going to do those children. Okay, here's a little thing on the size, right? Actually, let's go and talk about the, well, we'll get there. We'll get there in a couple slides. The space required is going to be the node, and then all of its children, and then this node and all of its children, which could be up to 26, and this node and all of its children, et cetera, right? So that's how the space actually comes out. This is called fan out, right? It's like a fan going out like this, right? It's called fan out, and the maximum fan out is limited to 26 because we're saying we're only doing characters in here, right? But it still takes up a fair amount of space. You can compress these a little bit. Okay? Look what I've done here. I actually know of a student who's one of the lab TAs actually who got a question about how do you compress a trie in an interview, right? So it was actually, and she supposedly figured it out too. She'd never seen it before, but she kind of figured it out. But the idea here is if you're at the end of a word and there's no children, just compress it all into one node. Okay, there's a little more work to be done, but in terms of space saving, you can do that. Okay, what this means is the little star now is like over the letter that's actually the word. So look at pit and pits, both words. Pit and pits, there's two stars because the star will be over the S, meaning it's a word, and the star's over the T. I'm not going to make you do a compressed trie. Okay, but if you want to, you can. We can actually compress this a little bit more. Can anybody see where we could compress it a little bit more even? Yeah, John.
At the CO and the FI.
Yeah, the CO and the FI, right? There's only one child there, so why not make the CO and the FI go into one node as well? So you can compress it even more like that. Okay, and it just means less searching, and then the actual size of the trie will be different. Again, you have to figure out how to store this and how to do the algorithms to figure out that you're at a node with extra characters, et cetera, but it's possible. Okay, it's possible to do. Okay, all right. So that's how we do the trie like that. Now, here's how we would actually build it. Okay. Let's talk about how we build these children. Okay, the children are kind of an interesting part of this, right? If you have a node here, okay, let's say it's a C, and then you add an O, right, an O in there, and then you add a CR because you're going to do crow or something, right? We said we can have up to 26 different ones of these, right? How should we represent those? There's a couple different ways. I want to know at least 3 different ways to represent those. What's one? An array of node pointers. That's a good one, right? So we can just have 26, and we know that it's going to be 26 because we fixed it. We said no numbers allowed, et cetera. That's one way. What else could we do? Yeah, Alice? A linked list. Sure, we could have each one of these, like this C has a little linked list on it, which points to the next linked list, which points to the next linked list. That's a good way. Okay. I think there's probably another way to do it. Those are 2 good ones, right? If we can't think of them, that's all right. What do you think?
Unless you're searching for your array linearly, just for choice, you should use this sort of hash table that helps just being subtracted.
Oh, you could use, yeah, there's other kinds of data structure we haven't talked about yet, like a hash table or something. Sure, you could do that. But for now, let's talk about it this way. What's nice about this method is that it's random access. Remember, we've got arrays that we can pick any point in the array and go immediately there. With the linked list, we can't. So this one, if we were searching for Z, 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 like let's say somebody put that in the tree, right, or in the trie, it would go like Z, and then go all the way down to the end of the linked list, Z, and then all the way down to the end of the linked list, Z, and it would take a little while to search that. You now all of a sudden have to do more searching. But that's not so bad. And if you did it right, if you knew the frequency of your letters, you could probably do that. Maybe the first letter is going to be T, and the next letter is going to be, or maybe the first letter is going to be E, and the next one's going to be A, and then maybe T, so that it's, the frequency. You could do that, and it wouldn't be too bad, right? There are lots of little games you can play. But let's concentrate on this right now. If this is an array, if each child of C is just an array of 26 children, right? Well, what we can do is we can assign each one of these an actual letter, right? So 0, 1, 2, 3, 4, all the way up to 26. 0 is going to be A, 26 is going to be Z, et cetera, and 1 is going to be B, and so forth. What's that? 25. Sorry, 25. You're right. 0 to 25. Thank you. OK, so we're going to have all the way up to 26 total letters, 0 to 25, and we're going to represent it this way. Here's the interesting thing about this. Letters, the letter A, and I'm explicitly doing it with single quotes, actually stands for what type of data? A character, a char, which really under the covers is an int, right? It really is an int, and it's an integer. And it turns out that there's a code for this. Okay, it's called the ASCII code, which ASC, yeah, that's it, ASCII code, which defines what all the numbers are. There's lots of different codes. The one we tend to use today is called ASCII. I actually have a little ASCII chart on my computer here. Of course I do, I'm a nerd. But so it's on here, and it tells you what they are. And if you hover over it, you look at A, and uh-oh, what happened? Ah, hang on. There it is. A happens to be 97. OK? So if A is 97 and it's an integer, what is 97 going to represent in our array? 0, right? 97 is 0. So if we are looking for some character, let's call it CH, and let's say CH in this case, let's say CH equals S, right? How are we going to know where in this array S should be? What do you think? How are we going to know where in the array S should be? We know that if it was A, we would say it's where? 0. If it was B, it would be 1. If it's S, where is it? How do you know it's 18? Well, OK. S, Max, what were you going to say? Yeah, watch this. CH minus A. We know A is 97. We know S is, if we go down here and we look at it, S maps to 115. 115 minus 97 gives you what? What is it? 18, right? And so that's where it's going to be, which is kind of cool. It means that if you have the character, subtract the character A, because it's an integer, out from it, and you will get the position in the array. Ooh, that's kind of neat. OK, that's actually pretty neat. Let's see. Let's walk through this, and then we'll see how that actually relates over here. We're searching for the word. OK? If we're searching for the word, well, the first thing we need to do is we need to set the current equal to the root. OK? Now, let's see. Is this going to actually work? If the current is the root, yeah, it's going to be the root is going to have one. It's not going to have a letter associated with it. It's going to just have children. OK? While current is null, pretend this is an integer. If the we're going to have a for loop. What's cool about strings is they give you these functions like length, which tells you how many characters are in the string. And they overload the bracket notation so that you can say SI, and that will give you the ith letter in the string starting from 0. So if we had the word cow, right, what does, and this was S equals cow, right? What does S1 give you? Oh, right, because it's the first one there. OK, so we can say it's OK. So we're going to go through the string, all the letters. We're going to find the child. In other words, figure out if that character is in the child. I'll show you that on the next page. And then we're going to, if we return null, it means that there was no letter there, and it means our word is not in the try. If the letter is in the try, then we need to go back and redo it again. The new current that we're checking is the letter, that node. And then we're going to check its children to see if the next letter is in there. Make sense? C-O-W. We're going to check, check, check. OK? And then at the end, when we finish all of the letters in the word, we have to make sure that it's actually a word. Because if we searched for C-O, but we have cow in the try, it wants to stop. It wants to look at that O and say, are we at the end of a word? And if we are, then we're going to be good to go. We found a word. If not, we return false. Questions on that algorithm? How to search through the try? Not that hard. You have to look at it a couple times. So it's not that hard. The find child method. Here's where we've done exactly what we talked about earlier. Find child some character, right? Return the children, which is the array of node pointers, at the character minus a. That bumps it to the exact location in the array, and that's the whole function. It's pretty easy. And if that's null, then you have to, then you know that it's not going to be a word. Okay? We didn't do insert. Insert, you have to create a new node. You have to populate its children, or you have to make sure its children are right and all that. But you have to, the find works this way. Okay? Any other questions on that? That's how the tries actually work. You will practice this in the lab on next week. Okay? Who was the one who said, you said you'd never seen Empire Strikes Back, right? You would have no idea what this means. That guy's named Yoda. All right, he's like a Jedi master. Anyway, he says do or do not. There is no try. But he doesn't say try, but anyway. Very nerdy joke. In the earlier class, I said you guys were too young to understand it. I went, oh, I understand Star Wars. So you're one of the few who didn't get this. OK, questions on tries. Kind of a cool data structure. I think it's a neat one, right? It's definitely a kind of an out of the ballpark one. It's different than the other ones. OK. All right. So here's what we're going to do next. We are going to start on, or we're going to actually do priority queues if my computer is going to not crash on me. It looks like it is. Let's try this again. Keynote. Whoops. Uh-oh. Uh-oh. Looks like I've actually crashed my computer. Let's see. No. How about this? No. Uh-oh. Yeah, well, we can't even do that. I can't type anything right now. OK. I guess I'm going to have to restart my computer. All right. Talk amongst yourselves for the next 2 minutes. Sorry. What's that? Nah, it's all right. I don't mind. There we go. If you don't have an SSD in your computer yet, this will amaze you. Actually, it's not, because it looks like it's definitely screwed up. Uh-oh. Oh, there it goes.
Is there a setting you can get that text button, the found text? User preferences?
You can do that. Yeah, you have to hold down a key, I believe. But OK. Opening everything up. I have a lot of stuff open, I guess. Yeah, Secretary of the Navy.
Yeah, I watch NCIS too.
What's that?
I watch NCIS too.
Exactly. I don't watch NCIS. I just know what it is. Come on, open up. No, what the? It's trying to open up, like it's trying to find Keynote. There it is. There we go. OK. What is going on? It's not open. Where? It's not open. It'll open now. I don't know. OK, we're back. All right, so priority queues. Don't do this. It's still trying to open stuff. OK. As I said, we're going to provide commenting guidelines for a deadline. There is a spell checker. So I mentioned on a couple of homeworks that I graded that you guys need to spell check your readmes. I didn't take points off if you had one spelling mistake, but if you had two, I took points off. Right? So you need to spell check your. You can do that if you want using. Here it is, a program called A-Spell. Now I happen to have downloaded the Declaration of Independence.txt, right? When in the course of human events, et cetera, et cetera. And we're going to run that through A-Spell. So what you do is you do A-Spell-C and then Declaration of Independence. And it brings up this fun little like text graphics thing. And it says, hey, I don't think usurpations is a word. And you're smarter and you go, it is a word. Right? So you hit the little ignore. And then it says it again. And then you find something. Dissolutions. Is that a word? I think it is. So it doesn't always pick the words out right. Harass. These days we spell harass with one R, right?
Yeah.
I'm not sure, actually. I think it's just I think it's looking for harass. So if you type one, it will fix it and then go on to the next one. It just goes on to the next one. It's actually a pretty quick way. Offenses. This is the British spelling of offense, because remember, those guys were British back in the day, right? They actually literally were. Right? OK, so we're actually going to call it offenses with an S. Neighboring, again, it's also the British spelling, etc. So you can do that. What's cool about this is that it will fix it in the document and then save your document for you, and everything's good to go. OK, kind of cool. They probably use some data structure. They might use a try or something to actually give you the suggestions. That in itself is an interesting idea of like, how do you get suggestions for words? Like neighboring, it may or may not be, like neighboring is nearby neighboring. It's off by one letter. So there's lots and lots of algorithms you can design that will that will check and see how many letters off two words are. And you might want to, if there's a word in the dictionary that's one letter off from the word you typed, it's probably a good idea to put that as a suggestion, et cetera, right? I'm not sure how it finds nippering or gibbering or whatever, right? But it's all based on like how the distance two words are apart, letter by letter. So kind of cool. There's lots of different algorithms you can do for that. Anybody ever wonder where the dictionary is? I forget where it is actually. Cat. Let's see. It's like user share dict or something. Hang on. Cat. There it is. User share dict words, right? And there's your user dictionary, right? If we look at I don't know why some of those words are in there, but if we look at the amount of words that are held in this dictionary, word count it, there's 479,829 words. That's a lot of words. First one is the characters. The second one's the line. No, sorry. First one's the line. Second one's the words. Third one's the characters, I believe. Yeah. Yeah. Yeah, so there's definitely some interesting words in that dictionary, but that's that. Questions on A-Spell? OK, you can use it if you want. Make sure you have no typos. OK, some of you guys are like, we've talked about this before. You don't like using Eclipse. You don't like using the IDE. You like using Kate or Vim or whatever, and I'm perfectly happy with that. You do need to learn how to use a debugger at some point. The nice thing about Eclipse is it wraps it in this nice debugger with all these GUI windows and blah, 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 right? In the background is this program called GDB. GDB, if you learn how to use that, you can do all the same things you can do in Eclipse. It's just command line. You just have to figure out how to use it. You can set breakpoints. You can look at different data structures, right? You can see what the data structure looks like. You can run it, you can change things as you go on the fly. It's pretty cool. Look up how to use GDB, right? We need to move away from like the comp11 cout and what's the other one? Carr, right? You want to kind of move away from that. Sometimes they're necessary. Like sometimes you kind of just want to print out and see what's going on. But many times a debugger will work 10 times better, faster, more efficiently, et cetera. OK, so learn how to use that. Look up GDB and how to do basic debugging. And if you don't want to use the Eclipse one, that's cool. OK. All right, priority queues. So this is the next abstract data type we're going to be dealing with. Okay? Sometimes we want to store data based on the priority of that data, right? Here's some real life examples, right? Emergency room waiting rooms, right? If you walk into the emergency room and you've got you tripped and hurt your elbow, right? And you're like, oh, I think I broke my elbow. And then some other guy walks in and he's got a knife sticking out his neck, right? Right? You're gonna that guy's gonna get served first, right? Because he's a higher priority than you. You don't want it to be first come, first serve in a hospital many times, right? Because of that. You have to sit there with your broken elbow for 4 hours before a doctor will see you because other people are getting shot, right? So, there's a level of priority here in real life, okay? So that's the sort of thing. Office hours, okay? So if a professor walks in while I'm talking to you in office hours, the odds are I'm probably going to stop our conversation and say, hey, what do you need, right? Because there's a priority difference there, right? Somebody in class today somebody was in my office hours today, and their phone rang, right? And the person went to go for their phone, and I'm thinking, oh, if the person answers their phone, that's a big deal. And they didn't. They turned it off and put it away. I didn't even look at it. Didn't even look who was calling. It was awesome. It was I'm like, whoa, there's somebody has manners in this world, right? And no, that was cool. And then of course my phone rang and I picked it up, but it wasn't the cell phone. It was a different. It was like an office call from the secretary. Anyway, but there's priorities there. Getting on an airplane. Talk about priorities, right? If you try to get on an airplane these days, you know how they do it in zones now. You can have you're in zone 3 or whatever, right? Last time I was in zone 2, I think 100 people got on the plane before me. Right? I'm like, what does the zone 2 means? It's trying to mollify me, right? It doesn't mean anything. I'm still a peon, right? I don't actually mean anything. Zone 2, right? It didn't matter. But there's lots of different prioritizations going on there. If you're first class, you're going to walk right on. If you're a special elite member, you're going to walk right on. Okay? Real life has lots of priority situations. A priority queue just stores information based on the priority, not based on the data that we're trying to store. Now, there may be a relationship between the priority and the data based on whatever you're doing to make the comparison, but in general, what your priority is independent of your data itself. Okay? This is fundamentally different than the other types of data structures we've been talking about. Okay? It's fundamentally different. Why is it fundamentally different? Because there's no position necessarily, right? We just start talking about we're talking about a priority which doesn't have to have a certain position in the list, or whatever data structure we choose. Okay? No notion of position. Okay? All right, so how are we going to do this? We have this thing called a key. It's a very straightforward concept, right? The key is what we prioritize by. Generally, the key is a number. Okay, and most of the time the key is going to be a number because that's easy to compare. Sometimes the key can be a word. Sometimes the key can be anything you define as comparing objects. In a second, we're going to talk about why objects are, why we have to have specific rules about comparisons, right? Keys don't necessarily have to be unique. You can have two keys or the same key for different data. In that case, you don't necessarily know which one you're going to get back when you ask for a key, right? You might get one, you might get the other. Sometimes you get all of them. Depends on the situation you're in. Okay? Your key can change. You got to be careful when it changes, but your key can change, right? And what happens then, for instance, let's say Yelp has a 4.5 star rating on things, right? And then they serve a bunch of bad food and a bunch of people rate it lower. The key might be based on their rating, and that could change. So that can change. All right? We can look at that. Okay? Keys can actually be more than one value. You can have a number of keys for some data if you want, right? If a passenger's on a plane is standby, you could have lots of different types of information going into what the key is. How much do you pay? If you're first class, if you're an elite member, you can get bumped onto a flight lots of times, right? Almost no matter what, right? Another thing about the key is it can be generated by a property of the object. Let's say you have the price of a book. Well, that may like your key that you're comparing things against might be based on the price of the book. Sometimes the price might change, and then you have to update the key, and you have to be careful. We'll get into details about that in a little bit. Okay. While I'm on the subject, Amazon.com. You know, you ever go to Amazon and you look at you search for an item, and the first one that comes up is like a 4.5 star rating or 5-star rating, and you go, wow, that looks cool, and 2 people rated it. You ever do that? Like you look and you're like, I don't want this one. The second one has like a 4.3 rating, but like 180 people or 1,000 people rated it. That's probably the one you want, not the one that 2 people rated. So I actually think Amazon, their key structure is a little bit backwards. Like they may have changed it recently, but for a long time at least they were doing that. They were just giving you like whatever the maximum rated one is, regardless of the number of ratings, which is probably not the best way to do it, right? They're prioritizing strictly on the rating, which is probably not the best way to do it. Okay? All right, so you can generate the key can get generated by the object, but you've got to be careful with that because if that property changes, your key is going to change. And we'll see what that is. Okay, as I said, most of the comparisons, what are you looking at? What's wrong?
Just a math intro with
Oh, you had math material? Oh, we were fine.
I already got past that.
No, we're not in math class. This is very simple. All I'm doing here is saying, how do we do these comparisons? There's got to be some rules. If you're going to come up with your own key comparison, if it's an integer, you just compare them. You say one's less than or equal to the other, and that's it. Sometimes you might have a key that's based on properties, and you need to be able to compare them explicitly. Okay, there's a couple of properties. I am not going to make you memorize these properties. Okay, but you do need to, you need to kind of understand them a little bit. There's a property called the reflexive property that says that k is always less than or equal to k. That true? I mean, if you've got two objects or 2 keys, or one key, it is either less than or equal to the other key. In fact, it's always equal, right? But that's one of the properties. Another property is if you've got 2 keys, k1 is less than k2, and k2 is less than or equal. Sorry, if k1 is less than or equal to k2, and k2 is less than or equal to k1, they have to be equal, right? That's a property. If you build your comparison wrong, this might not be true, and then you've got a problem. And then finally, you've got this transitive one, which basically says if k1 is less than k2 and k2 is less than k3, k1 has to be less than k3. Pretty simple, less than or equal to. Okay? If you satisfy those comparisons, you will have no contradictions when you do your ordering. Okay? What that also means is that we now have a relationship among those keys. You could have overlaps. Like if it's the same key, they could be like this or they could be like this, like if they're the same number. So you don't know which exactly there is. But otherwise, you know that there's a linear relationship here. What does that mean? We definitely have a smallest key. Okay, isn't that true? If you order all the keys, you're going to definitely say, I have a smallest. You also have a largest, but you definitely have a smallest. Okay? It could be ties for smallest, but at least one of them, you pick it out and you say, that one's smallest. Nobody's going to disagree that that one's one of the smallest, if not the only smallest. Fair enough? Okay? That's what we're getting there. Now, why do we care? We care because a priority queue has these associated keys, right, that are put in when you put them into the data structure, that they're there. And the key determines a priority, and we care only about one of those keys. We will call it the minimum or the maximum, but we're going to stick to minimum today. Okay, that's it. We're going to have the keys, which are going to go in, and we're going to be able to get them this way. So a priority queue is an abstract data type. If it's an abstract data type, we have fundamental operations. Here's what they are. These will look somewhat similar to both stack and queue. Okay, this is called a priority queue. Okay? You can insert an item into the queue. You need 2 things to insert an item. You need the key, and you need the item itself, like the element itself. Okay? Insert item. You can find, as I said, you can find the minimum element. That tells you which of the elements has the minimum key. All right? And then finally, you can remove the element with the smallest key. This is kind of the difference between like pop and top, right? This is like your pop. This one's like your top. This is like your pop. It's kind of like that. This one just says, hey, what's the one that's the minimum? This one says, get rid of the minimum. A lot of times we'll combine these. Remove min will actually give you the minimum and remove it. But in this case, we're just going to break them up. Okay? Those are the major ones. You have to implement those. These are some ones you don't have to implement, but you should probably. The number of elements in the priority queue is empty, of course. The minimum key, which doesn't give you the element, it gives you what the number of the minimum key is. That might be important. Why? Let's say you walk into a hospital and you've got a broken elbow and they give you a number, you give you a number 3 and you're just about to get served because you're the minimum, and then the guy comes in with the knife sticking out his neck. What should his number be? It should be less than 3, right? Because he should have a higher priority than you. Okay, and a higher priority is like the lowest number in this case. So you need to know what's the lowest number so far. Oh, it's the guy with his broken elbow. Well, let's put neck bleeding dude at a lower priority, or a higher priority, lower number. Okay, but that will give you the actual key number name. Okay, don't worry about the fact that it's a reference. You just can't change. You might get the key. You just can't change it. That's kind of what that means. But it's not. It says important, but it's not quite as important as it says up there. Okay.
Comes in with the smaller key already then?
Say again?
So the neck bleed guy, he would come in.
He would go in with a smaller key, yes. Yep. He would, if he's got a higher priority, he's going to come in with a smaller key. Or a higher key, depending on the way you define it, but it doesn't really matter. We're going to define it as the minimum. Okay? All right. They are sequences, but they're, again, much like the stack and queue, we don't have to worry about all that other stuff. Insert before, insert after, add index, all that baloney. We don't need anymore. We need one insert and one delete function. That's it. Okay? Which means hopefully we'll get good asymptotic performance out of it. That's the idea. Okay? Here's the example. Now, the code you have will print out this example. So later you can maybe look at it if you want. It's also online. But here's what we're going to do. I'm going to have a priority queue, and I'm going to start inserting some things, and then I'm going to start removing them, and we'll walk through it. Okay? First thing I'm going to do is insert 5a, 5 being the priority or the key, a being the element, right? What's our priority queue look like? 5a. No rocket science here, people, right? Now I'm going to insert 9. Now we've got 5a and we've got 9c in the queue. Easy. Let's say I do 5 and then I insert 3. 5a, 9c, 3b. I don't care where 3b goes in here. This isn't, right now this is unordered. And as far as our abstract data type is concerned, it doesn't care what this is underneath the covers. Ordered or not, it doesn't matter. Does not matter. Okay? All right, let's add one more, which is 7. If we add 7, it looks like this. No trickery here. This is pretty simple. If we say min element, it's going to give us b, because it's the minimum keys element. That's what we get returned. Okay? Min element gives us the element, not the key. It gives us just the element. Okay? If we say min key, that gives us the 3. No rocket science there. If we say remove min, right? If we say remove min, notice the 3 is now gone because it found the minimum one and it removed it. Okay? If we say the size now, it's 3, of course. If we say the min element now, a, remove min will take away the 5. Right? Remove min again takes away the 9. Remove min again takes away the 7. What if we do remove min again? Yeah, segfault. Error, right? You'll get an error of some sort. Right? You should check this if it's empty or not before you try to remove. Right? And is empty will be true. Okay? All right. So everybody get what the priority queue is supposed to be doing? Yeah? All right. Pretty straightforward stuff. Let's implement one. Here's what you've got on your paper that you got. Anybody not get the handout still? Come on up. It's right up here, Carly. Okay. All right. On the handout, it's like lots of code, but you don't need to read most of it now. Okay. if you go to, I'll wait till everybody picks it up. Okay, go to line 87. That's where this is defined. Okay? This is your struct, which is called a priority object. Why not? We'll call it that. And what does it have in it? It has a key, which is an integer, and a string, which is the element. This is the differentiation, right? We don't care what the string says. We don't care alphabetical order for the strings or whatever. We just care what the ordering for the key is. Okay? The next couple lines down is the rest of the H file here. Okay? It looks a lot like the abstract data type that we defined earlier. Right? You've got size is empty, insert item, min element, min key, remove min, and I put a print, like a pretty print function in there to print out what it looked like on the board. Okay? The rest of it is the private methods. This looks a lot like a dynamic array because that's what it is. Under the covers, it's just a dynamic array, right? And you have to have a capacity and a size and expand and all that. And we've got this other little helper function called min index. You don't have to have that, but I put it in there for a reason. You'll see. Okay? Okay. Go down to line 130. Here's our insert item function. Okay? If this is an array, where should we insert items into an unordered array? Yeah, the back, right? So it makes sense that we're going to have an array here. And if we're going to put some items in here, let's put the following things in here. 8, 4, 2, 7, 9. Okay? Okay? If it's unordered, it goes 8, 4, 2, 7, 9. And we might have to expand in there, but that's it. Okay? That's kind of nice here. What's the asymptotic complexity of this? Constant, right? Just insert at the end. We don't have to move anything. We don't have to change anything. We don't have to go through all the things. Woohoo! This is awesome. We're already doing great when we just have to insert with order n. Or order 1, rather. Constant behavior. Okay? All right, go down a little farther to the I guess 138 is where it starts here. Next page. How do you find the minimum element in an unordered list? Josh?
Well, you'd have to have some sort of variable to keep track of the ones. You go through each element in the array and check each one.
Yeah, that's the key, right? You have to go through each element in the array and check. In order to find out that 2 is the minimum, I have to start with 8. I'll just immediately set 8 to the minimum and say this is probably the minimum so far. Well, it's definitely the minimum so far. And then I check the next one and say, is 4 less than 8? Yep, 4 becomes the minimum. Is 2 less than 4? Yep, it becomes the minimum. Is 7 less than 2? No, 2 is still the minimum. Is 9 less than 2? 2 is still the minimum. 2. But I had to go through all of them. What's the asymptotic complexity of this? Linear. Boo. Right? We don't like linear. But it's pretty simple. It's just a for loop, but it does have to go through all of them. No way around it. Can anyone think of a way around it? What do you think, Max?
Running minimum index.
Keep a running minimum index. In other words, have a min, and then when you're inserting, say, is this one the min, make it the min? OK. But then you have to find the second min when you have to update min, right? How do you find the second min? Walk through the whole list again, right? So yeah, that's a good idea, but you only get the benefit of once. The time I could think that might be better is if you have parallel processes going. And you always want to keep them in, return it immediately, and then in the background maybe update your minimum. But if you're trying to get lots of minimums out, you're going to lose in the end that way too, because you got to wait till that is done. Did you have a question or comment?
Well, I was thinking you could keep an array of mins. And as we put them in.
You mean keep an ordered list?
Kind of.
Ah, there you go. We'll get to that next. Yeah, an array of mins. Yes, that would be an ordered list, which would be next. Good call. Good call. OK. All right. So anyway, pretty straightforward, but we still say boo, right? Because it's linear behavior. Not so good. All right. But that's to get the minimum index. If we want to do remove min, what do we have to do?
Find it first again.
Yeah, we have to do find it first again. Oh, we have to find it first, right? If we're going to remove 2, okay, we have to check and go through the whole list and say, okay, index 0, 1, 2, 3, 4. Index 2 happens to be 2. Index 2 is where we want to remove it, and then remove it from index 2. How do you remove from a dynamic array? What do we have to do? Yeah? Replace it with the 7. OK, so 2 goes here, 7 goes here, and then what? Then you have to do this. And then 9's there. And then update size. That's one way to do it. Then we would be 2 times n. We would go through basically, or we could go up to 2 times n. What's a slightly better way of doing it? Let me re-erase this again. And 2, what was it? 9, 7, 9? 7, 9. Luckily I can do left-handed numbers. Yeah?
Maybe erase the 2 and then put the 9.
Yeah, it's not ordered, right? Do we care that 7 and 9 are now going to be in a different order? No, right? So you can just take 2, replace it with 9. In fact, you don't even need to delete 9. You just update the size. But we'll do it, kind of pretend like we're updating the size, right? But you just swap those two. So it's actually, you don't have to go through the list twice. You might think you do, but you don't. And that's what's doing here. Whatever your minimum index is getting replaced by what's at the size minus 1, and then you're decreasing the size like that. Okay? So you can do it that way. Okay, it's a little tricky maneuver, but for an unordered list, it's fine. Okay, for an unordered list, it works just fine. Okay, what's the asymptotic complexity of this? What is it? N again, boo. Right? Why? Because you have to find the minimum index, right? And that takes order n. This part's a constant, but this part's order n. Not so great. Okay, let's do this. Let's create an ordered list. All right, that's going to fix all our problems, right? Let's see. Okay, if we keep an ordered list, we're going to have to figure out how to keep this list in order. Okay, this falls under the topic of a little topic called sorting. Okay, we're going to have to sort this list as we add numbers to it. Okay, now we're going to sort this so that the last one is the minimum. Okay, so it's going to go backwards down. It's going to be the biggest over here, the smallest over here. Okay? This is actually down on line, let's see, line 271. I guess 273 is where it really starts. Okay? Let's just do this and see how we might do this. How it might work. If we're going to insert 8, and we're going to keep this sorted from biggest to smallest, we insert 8, and it just goes there, right? Nowhere else to go. It's going to go right there. If we insert 4, it's going to go here. This is probably a bad example, because let's do it this way. Let's put 9 in and then 4 at the end. 8, 9, 4 at the end. No, we'll do it this way. I just want to make it a little bit to 8, 2, 9, 7, 4. There we go. OK. 8 goes in, then 2 goes in, and it's going to go there. How did we know that it's going to go there? Because it's less than 8. So basically, we started at 8, and we said, is 2 less than 8? Nope, it goes there. OK, how about 9? Which side do we start on? It actually doesn't matter. I like to start from the end, because then you're going to keep going in one direction. You could start from the front, but then you're going to have to start from the back to move things over. So I like to just start from the back and go that way. You can do it whichever way you want. Just make sure you do it right. Okay? So I start at the back, and I say, is 9 greater than 2? It is. So 2 is going to have to move this way to make room for 9. So I better put 2 there. Is 8 bigger than 9? Or is 9 bigger than 8? Yes, so 8's got to move. So we put 8 here. We're done. So now 9 has to go here. 9, 8, 2. Let's look at 7. 7 greater than 2. You're going to have to move 2. Is 7 greater than 8? No, so 7 goes right there. See how this is going to work? It's called an insertion sort. And what you're doing is you're basically going through the list. When you get to the one you want to, when you get to the right place, put your number there and move everything else out as you go. Okay? And then 4. Is 4 bigger than 2? Yep. So 2 moves over here. Is 4 bigger than 7? No. 4 goes there. And that is now a sorted list, and we're good. What's the asymptotic complexity of this? Yeah, it's n, isn't it? Right? It's n for a list that's starting from thing. Yeah? Question? Oh, no, OK. Yeah, in this case, the asymptotic complexity of this is actually n, and it's not the best way of doing this, right? OK, it's actually you have to go through this. I mean, it's a good way of. It's not the best sorting method, but it gets you through the list. But you do have to worry about the fact that it's order n, right? Boo. OK, we don't like that. Okay, we don't actually like that. In worst case, that's actually kind of an average case. What's the worst case that could happen here? You kind of have to. Well, actually, you basically have to go through the list once. So for every insertion, you have to go n, right? For the whole list, it's going to be n squared, as it turns out. But for each individual one, it's n. Okay, so that's not so great. Okay, we've lost out something there. Where have we gained, though? I mean, to keep it sorted, we have a little problem, right? And we have to do all this, and that takes a little while. But look at where we've gained. Okay, min index. What's the min index up here? Yeah, well, the min index is 4 because it's the size, minus 1, right? But that's the minimum index. Boom. We didn't have to do anything else. It could not have been any of these other ones because this is a sorted list. OK? That's awesome. It means that we have one operation, which means what's the complexity for this? Constant. OK, so this is constant behavior. Woohoo! OK? In fact, the min element is exactly the same function. Now it's just this is only takes the min index takes one operation, which is awesome. What about remove min? How long does that take? What is it? Constant. You don't have to do anything. Basically, all you have to do is change the size. Like that's about as easy as it gets in C++, right? Change the size, you're done. What's the complexity of that? Constant. Yay. OK. So, hey, everybody wake up who's sleeping. Knuckleheads. I don't know why this stuff is definitely like trying, but try to stay awake. All right. What's that? Yeah. So we've got order constant behavior for this one as well. So we've lost out on one part, we've gained on another. In other words, this is what we end up with. Okay? For our unordered list, okay, inserting is easy. Takes constant time. Minimum element takes n time, right? It's linear. Remove min takes linear time. If we go and we say, let's order it, well, you take the hit up front in this case, right? It takes n time to actually put the item in the queue, in the priority queue. But then when you want to get out the minimum, it's constant. And when you want to remove it, it's constant. Which is better? Why is the ordered better?
Two of those things are constant versus one.
What if I had a situation where I had all this information and I needed to put it in the list, and then I was going to do 10 removes because I want just the top 10? Which one's going to be better? Right? Unordered list is going to be better in that case. right? We're going to take 1 to put all billion of them in there, and then it's going to take 10n to get the top 10 out, and then we're done, right? So there are cases. It all depends on your usage case. It all depends on what your usage case is. In this case, can you think of a time when we might want to use an ordered list? What's a good usage case for that? Yeah.
You're taking stuff in and getting rid of stuff at equal amounts.
Yeah, well, equal amounts is maybe. Equal amounts probably doesn't really matter between the two. But let's say you have a whole bunch of information, and you're going to put it in the database, and then you're going to do lots and lots and lots of mins and removes and all that, right? Then, yeah, then the ordered list would probably work a little bit better. This is the case where, let's say you're Apple and you want to, or you're Google, and you want to set up your database, and then everybody pulls data from it. Like, that's where you can take a lot of time up front. It doesn't matter. Google could care less how long it takes to actually index your data, but they want it to be really fast when you get it out. Why? They want this sort of, if they're going to have to take a hit somewhere, they want to take a hit when you're building the index, not when you're getting the data out, right? Okay, so those are some of the times you'd want to do that. Now, with a dynamic array, okay, this is actually all right behavior. It's not great. I mean, all these linear behaviors in here, trust me, if Google tried to do anything with their search with linear behavior, they would lose. They would not be Google, right? Because you don't like linear behavior. It's still too slow for what we want. We want logarithmic or we want constant. Yes, there's some constants floating in here, but it's not amazing. Okay? Next week, we will start talking about a different type of priority queue data structure, and it's going to be much better than this. Okay, much better than this. You'll be able to do all these operations in better time than what's available to us here. Okay, this is kind of all set up for a better data structure to use for a priority queue. Okay, questions? Sorry if that was boring today. I know a lot of people fell asleep, but I'm sorry about that. It's the weather? Maybe it is. I don't know. Questions on priority queues? Questions on keys? Questions on any of that? All right, I'll let you guys go a little early. I shouldn't. I should give you a pop quiz. Falling asleep. See you guys later.